Now, if I want to find 5x minus 2 cubed, all right, what that's saying is this. That's the first thing you need to understand. 5x minus 2 cubed means I have 3 of them. Now, if you look right here, can you tell I took, like, let's say the first 2 or the second 2? Do you notice I took a pair and I did a multiplication of the pair? When I do that, if you combine these like terms, don't you get that right there? If you combine these terms, you'll get that. And then you left with one of the 5x minus 2's that hasn't been multiplied. Then you have to do another multiplication of a 5x minus 2 and this. And when you combine these like terms, you get the answer. So you're basically doing either FOIL or a box twice if you have a cubic. Now the question is, what if that was a 4th power? Can you tell you'd have to do this 3 times? And what if that's a 5th power? Do you see how it gets really, really ugly the higher the power gets? And that's, we're going to show you a shortcut. When this power starts getting bigger and bigger, this method is not pretty. We need another shorter way of doing it, a cleaner way to take care of larger powers. But for this one, this is doable. But with the shortcut we're going to show you, you might even want to use a shortcut for this one. It's just the shortcut in this one, when you're doing the 3rd power, is kind of a wash, depending on your perspective. But let's talk about the shortcut. Now, what you see here is confusing. There's something called Binomial Theorem, which allows you to do binomials with higher powers. A 5th power would be terrible to do FOIL with. A 4th power. A 3rd power, not bad. You can use FOIL in boxes. But these ones that start getting really ugly. Now, looking at this, it looks really ugly at first. But let me show you how this theorem can help you do these problems. First of all, we have this Pascal's triangle that we learned to kind of create. And what you do is whatever the power is, you kind of go down Pascal's triangle to find it. Once you know it's a 5th power, you use the 5th, and you use 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. Do you see that? Hopefully. So again, you have the 1, 5, 10, 10, 5, 1, 1, 5, 10, 10, 5, 1. Pascal's triangle gives you the fronts of each piece. Another thing you hopefully notice in this answer is, do you see we have the 5th power again? That told us we're using this one, correct? Do you notice how the first one starts with the 5th power? Next, do you notice how the powers on the x's are dropping by 1 as you go to the right? But the y values are increasing by 1 to a 5th power here on the y's. So the first term, do you see you start with the 5th power, and on the y's you end with the 5th power. Do you also notice that, do you see this is a 5? Is 4 plus 1 5? Is 3 plus 2 5? Is 2 plus 3 5? Do you see how the powers always stick with the 5? Again, the first term starts with the 5. The last term ends with the 5, and they kind of cross each other. And we use these numbers on Pascal's triangle to be the front of it. So to do this problem, I have a 4th power. So do you see how now we're going to go down here to the 4? All right, so I'm going to use a 4 here because of the 4th power. And aren't I going to use these numbers now? Do you see them right there? 1, 4, 6, 4, 1. Okay, do you also see this right here, 2x? Do you see how we're using 2x repeatedly as the first term? And do you see this right here, we're using the -3 repeatedly. Okay, so we first start with these numbers as the coefficients of each piece. Then we take the 2x, and you see we started with the 4th power, then we went to a 3rd power, a 2nd, a 1st, and a 0 power. Then I took the second term, the red here, -3, and I start with the 0 power and work my way all the way to the 4th power. It's a pattern. It's interesting. It saves time. Then you have to clean up. So everything underneath here is just me cleaning things up. Hopefully you know that anything to the 0 power is 1. And hopefully you know that 2x to the 4th means 2x times 2x times 2x times 2x which would be 16x to the fourth. All right, and then if we clean this up, if you multiply all that, don't you get this? All right, if we go here, right there, negative 3 to the first is negative 3. 2x to the third is 2x times 2x times 2x, which is 8x cubed. And if you multiply all that, don't you get this? Here, 2x squared, are you okay? It's 4x squared. Negative 3 cubed is 9. Multiply all that, you get 216x squared, and so forth. Just keep the pattern going. Just remember, 0 powers are 1s. Watch out for negatives. Watch out for multiplying multiple pieces. And you just simplify this as 81, simplify this as that, and you are done. It cleanly, pattern-oriented, less space for a whole bunch of multiplication and mistakes to do a binomial to a certain power. Now, for this last problem, it's a third power. So you could FOIL. It would actually work. It's easier to, we want to use this binomial theorem thing. So third means I stop at 3, so I'm doing 1, 3, 3, 1. 1, 3, 3, 1. I take the first term, x squared, and I start with a cubed. And I start with 2y cubed, and I start with 0. And then I slowly go from 3 power, 2 power, 1 power, 0 power. And I go from 0 power to 1 power to second power to third power of the first and second terms of the binomial. Then I get to just clean things up. As you can see, I just clean them up. Clean up this, clean up this, clean up this, and then clean up again, and clean up again, and clean up. It's just a lot of cleanup once you see the pattern. So the key is whatever the power is, you go down till you find that power, whatever it is. Then you go across. Those are the coefficients in front. Okay, so a third power is on this one. And then you take each term, starting with that power on the first term, and they should bypass each other because one's dropping by powers, one's increasing by powers. And it will take care of multiplying very large binomials for you. I think it's easier than foiling or box, whatever method you want to use with that.